Okay, hello all. I want to actually start by thanking my co-authors. They all really helped me out a lot with this. And also, of course, I'm starting by thanking the Lunar Science Institute for giving me this opportunity. Sorry. One more thing I also wanted to say was that I am going to very briefly talk about the debate, really. The debate is now not whether lunar water exists, if water exists on the moon, but it's rather, where is this water? Is it in the moon, outside of the moon? What's going on with it? And I'm going to briefly touch on all the water that we know about, but I will, of course, be focusing mostly on my favorite lunar water. Okay, so you know, here at the Lunar Science Institute, anybody who's a participant here knows that we are concerned with of the moon and on the moon, from the moon. But at the Lunar Science Natatorium, we are concerned with in the moon, on the moon, and around the moon, for lack of a better preposition. So starting with in the moon, there was a recent work by Saul et al. And Hari et al. Looking at the green, Apollo 15 green glasses and the Apollo 17 orange glasses, and measuring OH abundance. And based on these analyses, they back calculated how much water would have to be inside of the moon to actually have pushed these pyroclastic volcanic glasses out and also have this residual composition. And they actually came up with the ancient lunar mantle having a water abundance comparable to the Earth's upper mantle right now. There has also been recent work studying or finding hydroxyl or OH in lunar apatites. So there's water in the moon. There's water on the moon. L-Cross has confirmed that there is water and other volatile components. They made direct measurements in the ejecta plume that was excavated by the impact into Cabeas. Also, hydrogen has been detected by Lunar Prospector and by LEND. And MiniSAR has been detecting buried water in the polar regions as well. And here we come to the part that I am mostly a fanatic of, and that is the water that is existing as a superficial layer around the moon. And I will also, of course, be focusing on the M-cubed analysis, studies of these. Although, of course, it was the information was first released simultaneously in 2009 by Sunshine et al. With epoxy data, and by Clark with Cassini-Vims, and of course Peters et al. With M-cubed data. So what does M-cubed see? M-cubed sees actually OH and water on the moon. And we do this by looking at the reflectance spectrum. And particularly, we're paying attention to this absorption feature over here. If the absorption feature is stronger at 2.8, that is more attributable to, forgot about that one, to OH. If it is a little bit longer wavelengths, closer to 3 microns, that is considered to be attributed to water. And then, of course, if it goes beyond the range of M-cubed, though, that would be water ice. So one of the things me and my co-authors wondered is there a and I'm sure many of you all wonder this too, is there a correlation between OH and water and mineralogy? And looking at this this new image that Roger Clark has put together from thermally corrected M-cubed data, he assigned the red channel to the 2 micron absorption feature, which is attributable to pyroxene abundance, and the green channel to that OH feature, and the blue channel to the 3 micron water feature. And as you see, it looks like the red areas, I mean, they're red, they're just red, they're not magenta, they're not white, so it's saying that they're just pyroxene and they're dry pyroxene. And I also need to point out that some of this looks a little ugly because of striping variations due to variations in the band depth with phase. And this is, we need to better improve the photometric correction, which is something we're still working on. Anyway, this apparent correlation between the OH or water feature and mineralogy is a little problematic and not quite so straightforward. There is an effect of albedo on absorption strength. And basically, this is work that has been done by Millikan and Mustard. Effectively, if you have two materials of the same water abundance, but they have two different albedos, well, the one that is brighter is going to look like it's got more water in it in reflectance spectra. They also pointed out, actually, that the presence of ilmenite in the sample will actually impose a positive continuum in the 3 micron region, which is going to even further exacerbate the problem of trying to actually quantify the water. And then they concluded that really to most accurately do this, you need to actually take that reflectance spectra and convert it to single scattering albedo, then remove the continuum, and in this way you can much more accurately characterize the OH or water abundance. And this too is work that the MCube team is working on in their continuing efforts. So we can't really look then if there is a correlation with mineralogy and water right now, at least, just yet. But maybe there is a correlation between space weathering and the apparent water abundance. So now I'm going to kind of hone in. I'm sure everybody's familiar with space weathering, so I'm just going to briefly mention the things that are actually really in what are the space weathering effects that I'm concerned with for how the effects it's going to have on the surface that M-cubed would see. And that is pitting by micrometeorites, which could actually create little holes where OH or hydrogen could get trapped into. The formation of agglutinates and glassy coatings on grain surfaces, and the formation of nanophase iron. So, is this a surface phenomenon? What I mean by this is this really a, I can't say. Let me get to my notes here. Okay. The idea here is that the solar wind delivers hydrogen to the surface. In the path where the direct sunlight is hitting, though, the energy is too high for hydrogen to actually be absorbing onto the surface. So, and this is mostly what epoxy saw, is that the hydrogen starts sticking, or the OH starts sticking as it goes into lunar dusk, sticks around to the night side, and as we come into lunar dawn, it starts sort of boiling off, if you will, boiling off. So, given this idea, there are two possible mechanisms for how there could be a relationship between hydroxyl, water, and surface maturity. And that would be one that is pictured down here. When there's a fresh impact that occurs, minerals are broken and you get these fresh surfaces that actually are active. They have a net charge on their surface. The solar wind protons stream in, see that negative charge, and they go and they adsorb to it. And you get what the reflectance spectrometer would be seeing as OH. If this is the case, then hydrogen sites would, then it would seem that the more fresh places would look like they had a higher OH abundance. And furthermore, as the mare and the highland surfaces both mature, the OH abundance would decrease. Also, fresh glasses, like pyroclastic glasses, should have a really low OH or water feature that maybe slightly increase as they mature due to some of the pits created by micrometeorites. The other side is that OH is actually getting trapped in nanometer-sized vesicles as the hydrogen gets implanted into the soil. And it's getting trapped in these vesicles that are formed when these glassy surface coatings are being formed on regolith particles. Since they are mostly transparent right there at the surface to the spectrometer would see this OH abundance, and it would also see that as the surface matures, that OH abundance would be increasing. Okay, in this image, we have the 750 nanometer reflectance from M cubed, and this is a maturity estimate, which is basically the how steep the slope, the continuum slope is. And then this is the 2.82 micron band depth parameter. We note that there is a really strong correlation between maturity and OH abundance, and that is that here the bright areas are the areas that are more that are fresher. The dark areas here means that there's a lower OH abundance. The more mature materials appear to be moister than the fresher ones. This tells us that something about space weathering is causing the surface to hold on to OH better. Swirls, of course. Swirls are extreme examples of space weathering. Here we have also M-cube data of Rainer Gamma, Gerasimovich, Mari and Genai, my favorite. This is the 2.82 micron band depth parameter. This parameter is consistently weaker on the high albedo swirls compared with the surrounding off-swirl areas. This says that the swirls are depleted in OH relative to their surroundings. Since the swirls are believed to be in areas where space weathering is retarded or they are fresh surfaces, then there's something about space weathering that is causing the surface to hold OH better. Water and pyroclastic glass deposits. The Mari and pyroclastic units stand out in the 2.82 micron band depth parameter as is very dark compared to the surroundings. This says that they are lower in OH compared with their surroundings. Here's a close-up zoom of the pyroclastic event itself, which is already low, and here is a fresh impact into the pyroclastic. And this fresh impact into an already low OH area is revealing even lower OH. It indicates that the fresh material has an even lower OH abundance. There is something here also being shown about space weathering that is causing the surface to hold OH better. Here are some examples from Roger Clark, and actually these slides come from the presentation that Noah gave at the Wet versus Dry Moon workshop. Here we have a 1.5 micron, reflectance image, and as you see over here we have a fresh crater, and up here we have this diffuse area in the upper right. In the 2.82 micron band depth, the OH measurement parameter, the fresh crater ejecta has regions where it's a lower OH, and the diffuse area is coming up really bright. I'll go back. Roger also makes use of the 3 micron band depth parameter. In this image he's showing where in that fresh crater there is actually a patch of water, and over here in the diffuse area there's also it's a water-rich area. These boundaries are also a lot sharper than they were in the OH parameter. And then where he puts them together in an RGB image, you can see that the fresh crater has here, it's pyroxene rich and it appears dry. Area is pyroxene and wet. And here we have that diffuse area. And here's another one. This one's really cool. Right? Just typical, really, really normal lunar looking background. 2.82 micron band depth parameter. These features appear, which remind us of swirls. And Roger calls them proto-swirls, which I love to pieces because they're linear. I'll take this one back too. I mean, just one more time. Keep your eye like on this, for instance. They're not there. There they are. And then in the 3 micron, or water, oh, I'm sorry, that's right. And yes, this is the RGB image, which has, again, the 3 micron feature. And Roger also has noted that he says it sort of looks like the protoswirls are water features, water-rich features that are diffusing into OH. The 2.82 micron band depth parameter is actually the best tool that I have seen so far for locating elusive swirls. So in some of the magnetic anomaly regions, let me say this again. Swirls have been identified at magnetic anomalies, but not every magnetic anomaly has an identifiable swirl. But with this parameter, we might be able to see them much better. And in this example in Mare and Genii, it's obviously really easy to find the lunar swirls here on the Mare. I tried really hard to trace them out as it goes into the highland regions, and I couldn't. I got lost between what was just the sun-facing side of a mountain or something. But since the OH band depth parameter requires that the thermal emission be removed first, and we don't really see some of those lighting effects. So we can actually use it to trace swirls into the highlands or where we can't otherwise see them. These are all swirls up here. And here is finally, oh yes, my conclusions, right. There is we have noticed that there is definitely an equator to pole water abundance variability and a probable leading and trailing terminator variability. For the same OH abundance, the high albedo regions will have a deeper apparent 3 micron absorption than the darker regions, so we've had a hard time, so far at least, determining whether there's a correlation between water abundance and composition. However, we do know that the mature regolith does have this like background OH, and we can't really characterize the background water so much. It's a little bit more complicated and variable. There is definitely something about space weathering that is appearing to make the OH stick. I like the idea that it's the water being trapped, or the OH, excuse me, being trapped in these vesicles as the soil matures. The high albedo swirls are depleted in OH, and depending on which school of thought you are with about how the swirls formed, it could be because these immature material can't hold on to OH, as we've shown for all these other immature regions, or the swirls are just not getting hydrogen because of the magnetic anomaly. There are some examples that we found of fresh craters that are wet, and when I say wet, I mean it's the 3 micron feature of water. So it does sort of make this a little bit more difficult to explain outright. There's obviously way more work to be done. I've kept this talk pretty short because I've only talked about one side of the debate. I'm not very good about talking about the other, so I'm hoping we can use the rest of the time to debate it. Shameless plug.
We have plenty of time to debate, so who'd like to debate? Rosemary.
Hi, you showed an image with an area, and I wasn't really clear on where it was. It had a large area that was depleted in OH, and then sort of a fuzzy area that had more water. Was that associated with a magnetic anomaly? Or,
I wish I knew. Unfortunately, I didn't think in time to contact Roger and ask him where these regions were located.
Okay, so Roger Clark would have these?
Yeah.
Okay, thanks.
Yeah, I'm really embarrassed about that. I'm sorry. I wonder where they are too.
There's a question right over here.
So the Apollo samples that were returned show that there's a correlation between the hydrogen abundance and maturity. And so I'm wondering, is that hydrogen that's detected in the samples the same hydrogen that's part of the OH, or are there multiple hydrogens in there?
Well, so was that hydrogen detected as just hydrogen, or was it detected as hydroxyl?
I mean, maybe somebody in here has actually dealt with the samples can answer that, but it comes off with the thermal. So I don't know if you can tell exactly, but it is surface correlated.
Right. I'm not exactly sure. I do know that Lindsay Keller told me that he didn't know at least of any measurements where they had at least known that they were tapping the vesicles and getting the hydroxyl out, if it exists in there, out of there. So, I mean, one of the important things here is that, you can implant hydrogen into the soil and maybe it's not actually reacting with anything there. But if it's not actually involved with an oxygen molecule in its intimate sense, then it's not going to look like a hydroxyl absorption feature to M cubed.
Do you have other questions? Oh, Yvonne.
Hi, well, George, I want to thank you for a very nice talk, and you're very brave to invite a debate at such a meeting like this. I also want to add that her shameless plug wasn't nearly shameless enough. The Workshop Without Walls workshop that she put up the last slide for, you can also get details about on our lunarscience.nasa.gov website. We invite everybody here to please participate on September 7th. We'd really like to have a good debate about this and get your side of the story, get everybody's view on what's happening here. This is a very interesting phenomena, and I really thank George and her co-conveners for the hard work they've done in putting that workshop together.
Yeah, I'd like to say that I don't care what your interest is in science. The lunar swirls are interesting to you.
Do we have any other questions?
Do I have to say something controversial to get a debate going?
Yes, but actually I have a question, although it's not a debate question, is that have you looked at some of the areas that some people argue may be special? Like Pete Schultz had a paper out a couple of years ago suggesting there may be some recent outgassing on the moon and such. Does that show anything special in terms of OH?
I don't know about the particular regions.
I think it was the Ina region? I think that was the name of it.
Yeah, not that I know of. I know that I know that Roger's gone around and looked at some regions, but these are the only ones that at least he's reported back to us about. I don't think he's holding on to anything, of course. I do know that he actually he's one of the co-authors in the Lunar Swirls paper, MQ data, and he did actually want to put forward the hypothesis that the swirls could be regions where there's outgassing going on. But it's not in the paper. It was mostly rejected by the reviewers, so I think he has to do a little bit more work on making that argument.
Other questions? Okay, well, thank you very much.